carbon dioxide in the air dissolving in your sample. Now, at 2,000, let's do this, 15, 16, 17, 16, 17, 18, 19, we're good. At between about 2100 to about 1850, about right here in this region, you'll see a little series of pumps. Sometimes they're symmetrical, sometimes they're not. And they're called the Fermi resonance overtones. This whole series of pumps here, these are what they're called. Better contrast. This series of pumps is called the Fermi, F-E-R-M-I, after Enrico Fermi, resonance overtones. As the name implies, it's an overtone of another absorption. Like an overtone in music, if you hit a middle C with your electric guitar, those of you that are musicians, and you've got a piano next to the amplifier, sometimes you can hear the piano strings vibrate in sympathy. And they're not always at the same C. It could be an octave lower or an octave higher. That's what's going on here. Overtones. Fermi resonance overtones. Again, they appear between about 2100 to about 1850. That number is not so important, it's the shape. And the shape is their little speed bumps. They're speed bumps. And they indicate aromaticity. Fermi, F-R-O, Fermi resonance overtones indicates aromaticity. All right, so there's a big hint. Now, the shape of these Fermi resonance overtones will tell you if you have a monosubstituted aromatic, a disubstituted aromatic, and furthermore will tell you if you have an ortho, meta, or para disubstituted. It'll tell you if you have a tri-substituted, and if it's a tri-substituted, it will tell you if you have a 1, 2, 3, a 1, 3, 4, or 1, 3, 5. I'm sorry, a 1, 2, 4. Yeah, a 1, 2, 3 or a 1, 2, 4. It'll tell you if you have that, what the substitution pattern. The other one is it could be is 1, 3, 5. It'll tell you which tri substitution you have. Now, how do you figure that out? You have to go to your book. In your book, in the very back page, I think it's 1132, 1130, something like that. In the back of your book, there's an IR table. There's an IR chart there that helps you decipher these things. That IR chart will tell you if what type of substitution pattern you have for your aromatic. Now, there's another thing you can use down here called outer plane bend, loop bend. We'll look at that. It also tells us about aromaticity. Okay. Now, probably the two biggest absorptions in IR spectroscopy, if you're ever going to get one on an MCAT, it'll be one of these two. This one, OH stretch, or this one I'm about to draw. 1700, and I think Julia, somebody, yeah, Julia, Miss Jackie said 16 to 1800. It's 1700. That's what I want you to learn. 16 to 1800 is too hard to remember. I want you to remember 1700. 1700. And it's the strongest absorption in IR spectroscopy. Very strong. It's not sharp, spiky, like some of the others, but it's a very, very intense absorption. It looks something like that. And this is a carbonyl or C double bond O stretch. Now why so big? Because this CO has a huge dipole. C double bond O has a big dipole. It has a resonance structure, and the resonance structure shows up down here somewhere. C double bond O stretch is I'm going to characterize it as strong. It's the strongest stretch in the IR patterns. How do you characterize it? How do you characterize the CH2 scissors? It has a notch. N-O-T-C-H. It always has a notch. Owing to the fact that CH2 scissors have two vibration modes. One is symmetric and one is asymmetric. But the notch on this particular one, as I've drawn it, is right here. The notch that I'm talking about is right here. So you always see something like that, some type of notch. Because it really is two absorbances superimposed on top of one another. One is symmetric and one is asymmetric. That's really all I want to tell you. If you're crazy enough to become a chemistry major, you have to learn what the names of those modes of stretch. Now, the next one is almost as important. And sometimes, guys, these are obscure. Sometimes these are hard to find. The next one is at 1380, 11, 12, 1380, right there. So it's right below this one. And it's called a methyl stretch. 11, 12, 13, 8. This one isn't very strong. It's not very intense. It's usually broad at the bottom and comes to a sharper point at the top. So again, this one is at 1380. It's a methyl, M-E-T-H-Y-L, methyl stretch. It's actually the methyl group opening and closing like an umbrella. Methyl stretch. It's medium intensity. So sometimes you don't see a real prominent absorption there. It's kind of weak. Now we're getting down to the end, guys. We almost have everything that we want about these absorptions. I'm going to briefly show you how to use them, then I have to move on. So this is a methyl stretch at 1380. M-E-T-H-Y-L. And at the next one we're going to look at is at 1100, about right here. About 1100, you'll see an absorption. It also has a notch. It's also notch. And this one's pretty strong. This one is a CO stretch. C single bond O stretch. It's at about 1100. Again, this is a fingerprint region, and all of these are so unreliable that when you shift it up or down, depending. CO stretch is also notched, as in notch, and for the same reason. It's a CO stretch, C single bond O. Now here's the weird part. You guys that always doubted resonance. Sometimes you see a little C single bond O stretch from the resonance form of the carbonyl. I swear. I've seen hundreds of them. Alright, now we're the last one, and this is probably one of the most important ones, if not the most important. That's 700 and 750. 6, 7, 8, 9. There we go. 6, 7. So it's 700 and 750. It's an OOP bed. OOP bed. And all of these are strong. So here's the one at 700. Here's the 700. Often the 750 is kind of part of that one, sort of like this. Okay. And anything below 1,000 is an out of plane bend. Out of plane bend. It's a C double bond C or an aromatic CH. A C double bond C or an aromatic CH. And as you know, those things are planar. They're flat. So it's hydrogen doing this, bending in and out of the plane of the ring or the double bond. So once again, out of plane bend implies that it's planar, and they are. Like that. And then you have another one about right there. And many times these things are conjoined. They kind of run together like this. Sometimes not. Sometimes they're well resolved. It just depends. All right, so again, 700, 750 is called an OOP, out of plane bend. Out of plane bend. It's OOP bend. It looks crazy, like a weird name, like I made that up, but I didn't. It's an OOP bend. This is also called, this region is called the out of plane bend of the hydrogens. Is called a waggle. W-A-G-G-L-E. I swear I'm not making these up. OOP bend, and it indicates monosubstituted aromatic. Very important. Monosubstituted aromatic. That means you have an aromatic ring, a benzene ring, with one substitute. Almost 3,000, but not quite. And this one, the C double bond C, just above 3,000. But typically, there's one almost always at 3080. Then some others maybe. And usually it looks like, I could have maybe misrepresented that a little bit. Let me redraw that one. And they often look like, I'm drawing these from memory, but usually my memory's pretty good about this stuff. It looks something like this. Sharp, spiky peak, and then another one like that. That's typically what you'll see. Let me just draw it a little better. But again, for this C double bond CH, you'll see a sharp, long one. And then another one like that, a doublet, often. Sometimes a triplet, sometimes a multiplet. And guys, for aromatics, sometimes these can be extremely small. It can be right up here, just like a big multiplet that's unresolved for aromatic. But usually you'll see what I just drew you. Now, it's kind of hard to see where the absorption is and where that line I drew is also, where the line stops and the absorption starts. So I'm going to change that line color to red. And the first thing when you get an IR is draw this line. The first thing I always did, I drew a line at 3,000. Why? Because I wanted to know if there's any double bonds in there, if it's all alkanes. It makes a huge difference. If I'm getting all normal alkane stretch, then it's all normal alkane. That means there's no double bonds in there anyway. Or they show 4 triple bonds. Okay, 2260, I want you to learn because that it's there. It's not. Here's the rub. It's not in your book. Why? Because in your book, it's done by professional spectroscopists, and they purge or sparge the sample with nitrogen gas before they run an IR. This is to get rid of all of the CO2. Or they mildly heat the sample in reduced pressure. They'll reduce the air pressure above the sample and gently heat it. And all the CO2 will go out of it. But the easiest way to do that is sparge it or put an air stone in there, a stainless steel air stone, into the sample, turn on the nitrogen gas, and bubble some nitrogen through it for about 2 minutes, and it'll take all the CO2 out. You won't see it in the book, but when you guys do one, every one of you will have it. And you can try it. I've seen students come up and go, look at the C triple bond C stretch. It's not a C triple bond C, even though it's close. Or they'll say, look at this, a C triple bond N. It's not a C triple bond N, I'm telling you. And everybody wants to characterize it because it actually shows up. It's there, it's pretty big, but it's an impurity. With FRO, only on one of the aromatics, and I think it's just plain benzene, looks nice and symmetric like this. If you look in the back of your book, it'll show you different patterns, what they look like. And none of the substituted ones are exactly perfect like this. Sometimes you'll see small bump, great big bump, small, and then a medium-sized one. I mean, it varies depending on the substitution pattern. This thing is a honking monster. It's big. This one always goes almost to the bottom of the graph, the carbonyl. 1600, again, this confirms this. These two go together. So usually when I see this, I go over to 1600 and try and find this. If I see this and don't see this, something's terribly wrong. And I've never done that. Always when I saw that, the C double bond CH stretch, I was able to find the C double bond C stretch. CH2 scissors and methyl stretch, very important, but sometimes hard to find because they're in the fingerprint region. C single bond O stretch, this thing can be up as high as 1200, above 1200, or it could be down as low as right at 1000. So it varies a little bit. It's in the fingerprint region. And the OOP bend, sometimes you get OOP bends with just an alkene. Sometimes you get absorbances down here and they're way, way low and you can't identify them. Let them go. If you can't identify them, just leave them alone. If it doesn't look right, it probably isn't right. These 10, OH stretch, C double bond C stretch, normal alkane stretch, carbon dioxide impurity, Fermi resonance overtones, carbonyl stretch, CH2 scissor, methyl stretch, C single bar to O stretch, and hoop bed. I think that's 10 or 11. And with those basic ones, you will sound very, very sharp. You'll sound like a very highly educated student in the field of spectroscopy. Now, how do you use this? We're running out of time, so I'm just going to go to the use. How do you use this? Here's you can learn these. And guys, on the exam, here's what you're going to have. You're going to have a real IR, one of my homemade drawings like this. You're going to get a real IR spectrograph. And it will have pointing here, like this will be question number 14, 15, 16, 17, 18, 19. And then, so there's 4 or 5. And then the legend, A, B, C, D, E, will be your choices. It'll have, OH, it'll have these 11, basically. So it's basically a matching these, the names of these stretches with the actual stretch on a spectrograph. Now, Julia, you like to find trouble, like to find little detail things that you want to ask questions about. Here's one that you'll run into trouble with if you don't pay attention right now. Not to pick on just Julia, but Brianna, some of you guys that call me and stuff, Rukshana, I want you to look at the bottom of each absorbance, like on this one. At the very bottom, there'll be a tick mark right here. So any absorbance that's big enough will have a tick mark on the x-axis. Okay? Now, in the upper right part of the IR, those tick marks will be identified. A number will be given. Like for this first tick mark, 3450. That's the first red tick mark. Second red tick mark. 3095. So it'll give you the exact absorbance. Whether or not you can read it on this scale is irrelevant. You can always find it up here. Third one right here. 2260 on the mark. I think it's usually right on 2260. This one, the next tick mark right here. 1705, etc. So guys, if you can't read the x-axis, if you're looking on the x-axis and for whatever reason you're unable to see exactly where that is, it'll have a tick mark by it. All of the ones that are on the exam to answer have a tick mark by them. They have a little mark like I just made here. And you go to the upper right-hand side, starting with the highest one and going down to the lowest one. It'll be listed in the upper right-hand corner. Are you guys follow what I just told you?
Oh, and Professor Laurie, just a question. It says, is it ferro resonance overtone or ferro? Like, what is that? The name above?
F-E-R-M-I. Fermi.
Got it. Thank you.
Enrico Fermi was the first nuclear physicist to build a nuclear power plant, and he did so at the University of Chicago underneath the stadium where all the people sit. It just struck me as funny just now. They built the very first nuclear reactor. underneath the stadium where all the people are, in case something goes wrong, you kill a lot of people. And he was also, he did a lot of research work, obviously, in IR absorption. And because of that, they named an absorption for him, Enrico Fermi. He's probably, of all of the people that added to this IR spectroscopy, he probably did the most. Okay, now I want you to have access to this page you just put in your notes, and now I'm going to show you how to use this. I'm going to try to do real fast two examples and show you how that works.
Professor Laurie.
6, 7, 8, 9, 10, 11, 12. We got it right. See how important it is? Just one little H can throw you off. Put these 4 pieces together, guys. There's only one or two ways you can do that. Take this 3-carbon piece, start over here, and do this. CH3, CH2, CH, OH. Put that OH up on that carbon because it had 2 open places. CH2, CH3. And look what I have. Look what I have, guys. If you guys never really learned nomenclature or structure or functional groups, you're going to be in a heap of trouble. P-N-A-N, drop the silent E for pentane, add the suffix O-L, pentanol. The OH is on carbon 3, 3-pentanol, or pentane 3-ol, either way. Now, does it have to be 3-pentanol? No. It could be 1-pentanol, 2-pentanol, or 3-pentanol. So we really don't know which one it is. It could be 1-pentanol, could be 1-pentanol, 1-pent-OH, or it could be 2-pentanol. 1, 2, 3, 4, 5. Could be 2-pentanol. 2-PENTOH. So it could be 3-pentanol, 1-pentanol, or 2-pentanol. Look at that, guys. We deduced a structure just from one IR. We didn't look at NMR, mass spec, none of that. Well, we got the formula from mass spec. All right, let's do one more real quick. I know it's 8 o'clock.
Wait, Professor Laurie, can I just ask a quick question?
Sure.
For the IHD, so you're looking at a specific page in the book, right? For the
Nope.
to get the 5 and this.
Nope. The book has something different completely in it.
So how did you know?
It's not very understandable, honestly. But the way they're telling you to do it in chapter 7, I think, they have a big, like 3 pages worth of crap in there, and it's still 2200 to 1850. 2200 to 1850. 1595, 1595, 1105, 700, and 750. Okay. So what's the first thing you do? What's the first thing we do here?
The IHD.
The IHD. Now I pointed to this because that's where everybody wants to go. You don't go there until you do the IHD.
And how did you get the, I know you're about to go over, but the first time you did it, I don't know where you got like the 12 over 2 or the 5 from.
B minus H over 2 minus X over 2
Oh,
N over 2 plus 1. That's where I got it. I plugged it in this.
okay, so that formula just stays the same each time we got it.
All right. So for C, I'll substitute the number 6 because there are 6 carbons. For H over 2, I'll put 8 over 2 because there are 8 hydrogens. For X over 2, I'll put 0 because there are no halogens. For N over 2, I'll put 0 over 2 because there are no nitrogens in this formula, plus 1. Okay? Now, 6 minus 8 over 2 is 4. So 6 minus 4 is 2.
Plus 1 for 3.
Something's wrong. I did something wrong. 5 and 3 is 8. No, that's right. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. No, I did that right. I did that right. What did I do wrong?
The math looks right. We have 6 carbons, 8 hydrogens over 2 is 4.
6 carbons. Oh, carbons. That's what's wrong. See, if you don't have the right formula, boy, you can really go nuts. 7 carbons. There we go. There we go. There are 7 carbons. Oof, man, I was getting panicky there. So 7 minus 4 is 3, plus 1 is an IHD of 4. Now, in your notes, whenever you have an IHD of 4 or greater, that tells you you have a benzene ring. Pretty much. Because a benzene has 1, 2, 3 double bonds, and the ring makes 4. Follow?
Yeah.
IHD tells us number of double bonds and or rings. And a benzene has 1, 2, 3, and the ring makes 4 IHDs. Index of hydrogen deficiency. So I'm already suspecting benzene. Now, 3080, that's C double bond CH. And if I have 3080, I should have 1600, and I do. C double bond C. 2990 means I have some normal alkane in there. I have some kind of alkane carbons in there, 1 or more. 2260 is CO2, impurity, so we disregard it. 2200 and 1850 is Fermi resonance overtones. And that tells me aromatic. So now I have 2 pieces of evidence. IHD of 4 and Fermi resonance overtone. That's called A forte evidence. It means all the more reason to believe. So I have 2 pieces of aromatic. IHD of 4 and this Fermi resonance. Do I have a 3rd piece of evidence? And that usually nails it. 2 is pretty good, but 3 is dead sure. 700 and 750 is an oop bend, and it tells me it's diagnostic for what? What is 700 and 750 diagnostic for? Now, this is very important that you know. Mono substituted benzene, usually. It's a mono monosubstituted benzene. Now that is gold right there. Now what? I'm going to show you in like less than 2 minutes how to put this together. Start with my formula, which initially was incorrect. C7H8O. And now I have this monosubstituted benzene. That means I can subtract away this. I can subtract a benzene ring with one open bond and 5 H's. Isn't that what a monosubstituted benzene is? So I can subtract that piece right there away. What's left? 7 minus 6 C. 8 minus 1, 2, 3, 4, 5 H3 and O. CH3O is what's left. So because it's what's left, I would write it also in red, because it would go towards the assembly of a molecule. It's what's left over. So I would have CH3 and O. So coming over here, I want to put together my two pieces. Here's what I have so far. Here's what I have. So what do I have? What do I have? You'd be surprised what answers you get here. Students will put CH3OH and say it's an alcohol, completely ignoring the fact that we did not get an OH stretch anywhere. We did get a CO stretch, but we did not get an OH stretch. So why would you put alcohol? Because we don't know any other functional groups. Matter of fact, most students, when they see oxygen, they assume it's an alcohol before looking at anything. They just go, hey, it's some kind of alcohol. Because they don't know any other functional groups. I'll give you a big hint. It's not an alcohol. So what is it? What's the only way you can put these three pieces together, guys?
Is it an ether?
Yeah. Has to be. There's no other thing it could be. So if it's an ether, now oxygen, most of you know, is divalent, means it has an open bond, and two lone pairs, like that. CH3 group means you have a carbon, open bond, and then 3 H's, like this. Now you have oxygen with two open bonds, so you can put in here. Put the oxygen here, open bond, with one open bond, and then what's left is CH3. It has to be this. It's the only thing you can put together. So it's anisole. Remember? We just did one on aromatics, right? We just did an exam on aromatics. It's anisole. That's what anisole would look like. Okay, so you guys kind of get the picture. I'll do another one, but I'm going to send you ASAP a worksheet. It has a lot of NMR on it. The NMR is what you need to learn very quickly. Then we'll have a couple days to review for the rest of the final, which is just some odds and ends and stuff like that. You'll have a spectroscopy exam on the day of the final, and then you'll also have one based kind of loosely on chapter 19, 21,